Alright, I wanted to do a quick rundown on rate laws, not integrated rate laws, just regular rate laws. Hopefully this is review, but the rate law shows the relationship between initial concentration and initial rate. So we'll have data that tells us concentrations along with rate. For the integrated rate law, your data would be time and concentration, but for the regular rate law, it looks like the data that is presented over here has concentrations and rate. So your normal rate law looks something like this. Rate is equal to the rate constant, K, times the concentration of something raised to its order, all right? The order shows the relationship between the concentration and the rate. It shows how the concentration affects how fast the reaction proceeds. If the order is 1, that means a double in concentration will double the rate. Second order means it's going to be related by the square of the concentration. So if you doubled the concentration, the initial rate would quadruple. A zero order reaction means that the concentration does not affect the rate at all. So for a zero order reaction, you would be looking at rate is equal to K times A raised to the 0 power. First order, you would have K equals A raised to the first power, and sometimes they leave the 1, sometimes they actually just erase it because something raised to the first power is just, the thing, whatever it was before. Second order reaction, the rate is equal to K times the concentration squared. Now, most of the time, you're not going to have just one reactant. You're going to have multiple reactants. So, when you have multiple reactants, the only thing that changes is you just add on to what you already had. So, in the case that I showed for the data over here, there are two reactants, A and B. And so, you'll have A raised to its power and B raised to its power. Now, it doesn't really matter what you use as the variables in the exponent. You could use x, y, whatever. A lot of places I've seen use m and n. I don't even, it doesn't matter to me at all. So, looking at the example that I have over here, there are multiple reactants. We want to find the rate law for that reaction. Well, since there's multiple reactants, we're going to use this. So that means that go ahead and just write it out as is. Rate equals K times A raised to something. I'm going to leave a space, and B raised to something else. Well, how do I figure out what the order is? Well, notice that in the data, they're always between two data points. Right here, the B is held constant, and right here, the A is held constant. So that means that when comparing this point with this point, the only thing affecting the change in the rate would be A. And you notice that as we double the concentration of A, the rate actually doubles. Now, it's not a perfect double. The data typically is not perfect, but it's really close. So that means that it is first order with respect to A. Now, looking at these 2 points, we hold A constant and B changes. So that means the only thing affecting the rate change is the concentration of B. And if you notice that the difference between these two, you're going from 0.025 to approximately 0.1, which is a quadruple. So that means this is second order with respect to B. Now, typically, you also will need to find the rate constant, which is K. So all you have to do in that case is pick a point. Sometimes they'll actually give a fourth point. Since I just kind of like made up fake data, I didn't actually do a fake point. So what you would do is just pick any of the points. It doesn't really matter. If you want to be really accurate, do it for all of them and then average them. And just plug it in. So let's just do the last one. The rate is equal to 0.096. That is equal to K. The concentration of A is 1. The concentration of B is 1. Okay. So you have 1 times 1 squared, which is 1, which means 0.096 is equal to k. And that's all you do. Like I said, most of the time they'd have another point that you could use to solve for that. But I hope that is a little bit helpful.